So here we have another infinite sum or series, and we're asked to find what it sums up to. So we want to remember this, that the sum of an infinite series, if it exists, is the limit of the partial sums. If we look at this sequence here, 2 over n minus 1 times n minus 2, this is not a very helpful form as it is right now for us to be able to see that it does converge and see what it would converge to. So we actually need to rewrite it using something that we learned in order to integrate, but now has other applications, which is partial fraction decomposition. So we have the fraction 2 over n minus 1 times n minus 2, and we want to rewrite this as two separate fractions. So it's going to be a over n minus 1 plus b over n minus 2. And so now we're going to solve for a and b by multiplying by the common denominator. We get 2 equals a times n minus 2 plus b times n minus 1. And so we want to pick convenient values of n so that we eliminate one of the variables and we can solve for the other one. So first let's pick n equals 2. And if we do that, we get 2 equals, this is going to go to 0, and so we get 2 equals b. Well, that was nice. If we pick n equals 1, we get 2 equals negative a, and then that goes to 0, and so this implies that a is equal to negative 2. So we have our a and b values, and now we can rewrite this sum as an addition of two separate fractions, and that's going to help us be able to find the partial sums. So that means we can rewrite this. We have the sum from n equals 3 to infinity of 2 over n minus 1 times n minus 2 is equal to the sum from n equals 3 to infinity of, let's see, our a is negative 2, so negative 2 over n minus 1 plus 2 over n minus 2. All right, so now that we have this in a more convenient form, I'm going to look at the first couple terms and see what's happening with the sequence in order to get the partial sums. So I'll write them over here. So if we pick n equals 3 because that's where our sum starts, and you can kind of see why we picked that, because if we start at like 0 or 1 or 2, then we're going to have some division by 0, which is a problem. So we're starting at n equals 3. And when n equals 3, we get negative 2 over 3 minus 1, which is just 2, plus 2 over 3 minus 2, which is 1. And when n equals 4, we get negative 2 over 3 plus 2 over 2. And when n equals 5, we get negative 2 over 4 plus 2 over 3. And we can kind of see here that this is starting to telescope, like in the last example. And so if we look at the fifth partial sum, s sub 5, then that's going to equal 2/3 and negative 2/3 cancel, 2 over 2, negative 2 over 2 cancel, and so what we have is negative 2 over 4 plus 2 over 1. So this first term here, 2 over 1, that's never going to be eliminated by anything else. But this term here is going to be the last term dependent on what our kth term is. So if we want to look at the kth partial sum, that's going to look like, if we use 5 as k, that's going to look like minus 2 over k minus 1, and then plus 2. So now we can take the limit of these partial sums and see what we get. Okay, so now that we've found what the kth partial sum will look like, we can take the limit of the kth partial sums. So we have that the sum of this series, and from n equals 3 to infinity of 2 over n minus 1 times n minus 2 is going to be equal to the limit as k approaches infinity of the k partial sums. And so that's going to be equal to the limit as k approaches infinity of negative 2 over k minus 1 plus 2. And so we're going to think about what happens to each of these terms as k goes to infinity. So as k gets larger and larger, the denominator of this fraction is going to get larger and larger. And this is going to go to 0, this first term. And then this is a constant. And so it's going to stay 2. And so we're going to get 2. So the sum of this infinite series is 2. I forgot